retaining wall in AutoCAD. Okay, so that is our lab actually. So in the CAD we have to draft and drawing and design also has to be covered. Okay, the concepts which we have seen in the previous lab sessions and lab sessions. So you could have known what you mean by cantilever wall. Okay, so cantilever retaining wall. So what are the types? Okay, so those are all the things we seen already. Okay, so we come by categories. Okay, so first of all, why we have to go for the retaining wall? So the retaining wall to withstand the backfill soil which is there in the hilly regions, not only in the hilly regions, in the abutments of the bridge construction. Okay, so abutment in the and the end portions of the bridge is called abutment. Okay, so for the construction and design of that abutment element, structural element, we utilize the retaining wall. Okay, so it depends upon the height. Okay, uh, we again come to the classification of the retaining wall. Okay, so first of all, so we have seen about the gravity retaining wall. Since it is not a reinforced concrete wall. Okay, it is just a typical masonry wall which is made up of the rubbles. Okay, rubbles in the sense massive stones. Okay, massive stones and the mortar. Okay, so with these two elements they construct the gravity retaining wall. You have to observe the height first. Okay, so based upon the site condition, if the height 3 meters, you can go for the gravity retaining wall. Okay, so you just decided the height first. So based upon the height, you construct the gravity retaining wall. So in case of gravity retaining wall, you need not to go for the design of reinforcements and all. Okay, just a rubble stone and the uh, and the uh, materials which is needed for the gravity retaining wall. So in case of gravity retaining wall, we are not cover the design portions. But why? Because it is not necessary that you should design the gravity retaining wall. Height deciding factor. After deciding the height, you can go for the construction in case of gravity retaining wall only. If you decide the dimension, that is fine. Consider the cantilever retaining wall, in which case we go for the cantilever retaining wall. If you need the height in the construction site from 3 meters to 3 meters to 6 meters, then you have to go for the cantilever retaining wall. Considering this category, we have covered the design of the cantilever retaining wall. So the case study which you are for the design of cantilever retaining wall, so our wall is almost 5.2 meters, I think. Okay, so if you cross verify your observations, you could have retaining wall is 5.2 meters. Okay, it implies you need the wall which is having the height of 5 meters. Okay, with greater than the height of 5 meters, then you are going for the cantilever retaining wall. Like the elements of the cantilever retaining wall. So what are the different elements of the cantilever? Can anyone tell what are the different elements of the cantilever retaining wall? Or we can say it as a parts. What are the parts of cantilever retaining wall? Yes, someone come with the answer. So we have covered the concepts already.
Heels and toe.
Yes.
Heels and toes.
Retaining wall. You can say it as a parts. So what are the parts are there in the cantilever retaining wall? Yes.
The toe, heel, stem.
Then slab is there, toe slab and heel slab is there. And if it required, you should design the key also. Key of the retaining wall also. You should consider the against the safety and overturning. If you require the key, so then you have to design the key retaining wall key also, and you should provide the key to the retaining wall. Okay, so this parts of the retaining wall. Okay, so I'll share the screen which shows the types of the retaining wall. Actually, this is the picture which shows the counterfort retaining wall. Okay, so we'll coming to the concept of cantilever retaining wall. So in that cases, we need the height wall height as 5.2 meter. That's why we design the wall as wall. Okay, so our height is almost 5.2 meters. So that's why we went for the cantilever retaining wall. So we have designed that retaining wall, and we have drawn that is we have drafted that retaining wall in is fine. So now we are into the third category, that is called counterfort retaining wall. Okay, so you can just compare what you mean by cantilever retaining wall and what you mean by counterfort retaining wall. Similarity between the cantilever and counterfort retaining wall. Why? Because what do you mean by counterfort retaining wall? You know, if the site condition demands the greater height, okay, greater heights in the sense if the 6 meters height, then you have to go for the counterfort retaining wall. Due to the increase in the height of the cantilever wall, increase in the height of the wall, increase in the height of the wall, the soil mass to be carried by the wall. So, for example, if you consider wall, soil mass will be filled. Okay, so likewise the soil mass will be filled behind the wall. Okay, so if the height is goes on increase, actually if you consider the cantilever retaining wall, yeah, but in case of counterfort retaining wall, the height the 6 meter, that is greater than 6 meter height. So therefore the mass of the soil to be carried by this per increase due to the increase in the due to the increase in the backfill of the earth. That is the backfill of the earth is nothing but the soil which is backfilled. Okay, so in other words, it has a backfill of the earth. Okay, so if you consider this one, the height is increased. Okay, so if you consider the parts of the counterfort retaining wall, there will be a toe slab, consider angle slab also, and there will be a stem also. Okay, so there will be no change in this. Wait a second. Someone is waiting in lobby. There will be no change in the parts. Okay, so the parts of the cantilever and counterfort retaining wall is same actually. Hill will be there in the counterfort retaining wall also. In addition to that, there is a counterfort support. Okay, so this is there, no? So this is the additional support which is provided. It is provided, you know, to support the wall and as well as the slab. Okay, so why? Because the height is increasing, the load to be carried by the wall is keeps on increasing. They are giving some supports at an interval of 3 meters. Okay, as per the guidelines, the counterfort is provided between the interval of 3 meters. Okay, so for between the two counterfort retaining wall will be 3 meters as per the guidelines. Okay, and the counterfort will be tied together between the stem. So the counterfort will be tied and the heel of the retaining wall. Okay, so then this is the way the counterfort will be provided. Okay, so the stem and heel of the retaining wall will be tied together. If you see here, they are given it as a statement. Okay, so the counterfort retaining wall are economical for over about 6 meters. Okay, so if your needs the height which is greater than 6 meters, then you can go for the counterfort retaining wall design. Okay, so I have said about the counterfort retaining wall. So while we go into the design part of the counterfort retaining wall, you know, so what is the procedure involved? You know, there will be no change in the design of the stem and design of the slab. Okay, so we have seen all those element design in the previous class itself. Okay, there will be no change in that. What are the changes will be there? Okay, so in that aspect there will be an increase in the height. Okay, so there will be increase in the height of the counterfort retaining wall. So that is the one predominant change which will be there. As well as you have to design the additional element that is called count. What I have shown you the counterfort part to you. Okay, so that is the two. So that is the two there in case of counterfort retaining wall design. Okay, so now what are we going to do? You know, we're going to design. We are not going to design the wall slab. Okay, so we are not going to design the slab as well as the stem, but we're going to design that particular counterfort support which is provided on the wall to support the wall. Okay, so we're going to do that part alone. Okay, screen for the design part, but the design procedures will be same. Okay, can I able to see the screen?
Yes, sir.
Yes, sir.
You see, right? Okay, so if you see, yeah, as I told already, the design parts are over for the stem, and design parts are over for the toe slab as well as the heel slab. Okay, now what we're going to do, you know, so we're going to decide the width of the counterfort. Okay, so the width of the counterfort can be decided based upon the assumption and stem also. So the width of the stem at the top, you know, 200 mm. Okay, so considering that width, so the counterfort width can be taken as 400 mm. So double the times of the, so that the counterfort are provided at 3 meters center to center. So I mentioned about this already. The distance between the two counterfort support will be 3 meters. Okay, and the subjected to the counterfort, you know, they are subjected to the earth pressure. So earth pressure is nothing but the soil is termed in the other words as earth. Okay, so the soil and the earth are same. There will be a soil mass though, so the soil mass tends to apply the load on the wall. Okay, so that is the earth pressure. Earth pressure will be there. Okay, that is the counterfort will be downward reaction from the yield slab. So downward reaction is nothing but if you see this particular line, I am drawing the line diagram. So this is a stem. So this is, and this is the toe slab, and this is the yield slab. Okay, like this will be there. Okay, so what are the forces acting on the counterfort? So the first force is earth pressure, and the second force they are telling, you know, downward reaction is nothing but, so the counterfort will be provided like this. Okay, the counterfort will be provided like this, and it will be tied together with the provided like this, and it is provided together with the base slab. So this slab is there, no, is trying to push the counterfort support downwards. Okay, so from the yield slab. Okay, so this is the yield slab and this is the toe slab, and the yield slab will be tied together with the counterfort support. So the what this yield slab will do, you know, so the yield will push the counterfort support downwards. Okay, we'll try to push downwards. Okay, so this will be carried by the, which will be there on the counterfort. Okay, so you have to consider the two different load condition, two different design the counterfort. So that is the thing they are doing. So the first thing is earth pressure, and the second thing is downward reaction from the yield slab. Okay, so this is the consideration. So after that we are going into the design. Okay, so you could have known. So design is based upon what? Okay, so all the structural element in most of the cases, the design is based upon the bending moment is calculated the bending moment is calculated based upon the bending moment, reinforcement calculations are done. Okay, so likewise there is a expression here to calculate the ultimate bending moment which is acting on the counterfort. Okay, so there is a expression here. So what is the expression? So it is given here. Okay, so this is the expression. The values in the sense height. Okay, so height which will be given, you have to decide the height now only. Okay, so you have to decide the height, and other than that you can substitute. There is a coefficient of I think. Okay, so if you substitute all those things, you can get the expression like this. Okay, so with that expression you can substitute the value of height considering the side condition and consider. Okay, so for example, if you consider the cantilever retaining wall, in that cases the height is given it as 5.2 meter. In the case of counterfort retaining wall, as I told already, so that's why the height of the wall is 7.8 meters in this case. Okay, the height of the wall is 7.8 meters in this case. Therefore, we calculated the bending moment. Okay, so ultimate bending, but at this point. Okay, so this is the point C. So where the stem of the retaining wall is meeting the base. Okay, so after that ultimate bending moment is nothing but the factored bending moment. Okay, so you are multiplying the bending moment into 1.5. That is a factor value like this. Okay, so this is the ultimate bending moment of the counterfort support. Okay, so this is the ultimate bending moment of the counterfort support. Based upon this only, you're going to decide the reinforcement to be provided in the counterfort support. Okay, so in addition to that, you need to provide the net downward earth pressure on the yield slab. Why? Because there will be a soil which is filled below the slab. Okay, so there will be soil mass which will be filled below the slab. Okay, so that pressure also you need to calculate pressure. So the given one expression here, so the weight due to the earth pressure. So weight due to earth pressure is nothing but, so 18 is the, so your 7.8 is the overall height. Okay, so by this you can calculate the weight due to the earth pressure plus, so weight of yield slab. Okay, so you have to calculate the self weight of thickness is 0.45 and the density is 25. Okay, so the density of the reinforced cement concrete is 25. Okay, if you consider this first expression, they are considered of the soil. Okay, but if you consider the weight of the yield slab, you are considering the density of the concrete. Okay, so depends upon the material, you have to vary your value. Okay, so depends upon the material, you can vary. Okay, so this is the downward earth pressure. Okay, so the first two expression is downward earth pressure. So after that, to counteract, to have the counteract action, you have to calculate the upward earth pressure also. The pressure will be calculated. So that value is 80.39. Okay, so therefore the net downward earth pressure on the yield slab at the point D. So D is nothing. Okay, so where the counterfort ends. Okay, this is the point D. At the point D, the earth pressure is, the net downward earth pressure is 71 point. Similarly, you have to calculate the net downward earth pressure on the yield slab at C. Okay, so this is the point C. In the same way, you will be calculating. So first you will calculate weight due to the earth pressure plus minus upward earth pressure at the point C. Then you will get the values like this. Okay, so then you will get the values like this. Okay, so therefore net downward earth pressure on yield slab at C. Okay, so pressure due to the soil mark at C point and pressure due to the soil mark at D point, we are done. Okay, so after the playing with the total, so this is the net downward earth pressure. We have to calculate the total downward earth pressure. How will you calculate the total? So you have to multiply the actual value which you have got. Okay. 71.26. In the second case, you got it as 7.75. Okay, multiply by center to center distance, that is 3 meters. Okay, so this is center to center distance, that is 3 meters. Total downward air pressure at the point C and at the point D. Okay, so that you are done, So after that, what is the next step? As mentioned earlier, the counterfort act as a T beam. Okay, of T beam, how it has been designed. Okay, so applying the same concept here. Okay, so applying the same concept here, we are designing the by utilizing the concept how the T beam is designed. Okay, so by using that concept, if you refer page number 96 of IS, in that case, there will be a one expression where it shows. Okay, so the bending moment of that flange section, the expression will code book and the page number also. Okay, so at the side you just take down page number 96 of IS 456 2000. Bending moment formula. Okay, so we'll give you the flange section bending moment formula. You just take down the page number. I'm repeating again the code book and the page number. Okay, of IS 456 2000. You just refer in that page number 96. In case of flange recession, so there will be expression for moment. Okay, already, so we have calculated the ultimate moment. Okay, so using that ultimate moment, all the values in that particular expression, except the value of T. Okay, so you substitute. So in case of moment also. Okay, so the moment is 2135.6 into 10 power of 6. Why 10 power of 6? So it is in kilonewton meter. Okay, so you are substitute the values in meter and mm. Okay, so that's why you are converting like converting the kilonewton into newton. For that it is 10 power of 3. Then you are converting meter into mm. For that it is 10 power of 6. Okay, so 2135.6 into 10 power of 6. Okay, 10 power of 6. So that is the moment value. So you substitute all the value except the, then you depth of the counterfort support to be provided. Okay, so this is the minimum depth of the counterfort to be provided. Okay, so then you have to go for the calculation of the actual depth of. So actual depth of the counterfort also you will be designing in further. Okay, so we'll cover that particular thing now. So just a second. So till now, if you have any doubt, you can ask me. Any doubts is there? So then we can go for the next step of counterfort support. Any doubts is there? Yes, answer me. If you don't have any doubt, you inform that also. Then we can proceed. We can proceed the class.
Yes, sir. No doubt, sir.
We can. If you want me to repeat any other particular concept also, I can able to do. Shall we proceed?
Yes, sir.
Okay. We can proceed our next steps. related to the counterport support design. Okay, so I'll share the screen for the next steps of the designs. While can I able to see the screen?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Okay, yeah. So this is the counterfort retaining wall, two-dimensional diagram. Okay, so this is the counterfort retaining wall, two-dimensional diagram. In this case, the height of the retaining wall, that is the height of the cantilever retaining wall is 7.8, and the width of the toe slab is 4.05 meters. Okay, so at some particular angle, the counterfort support is tied together with the stem as well as the slab of the retaining wall. Okay, so it is tied together like this. Okay, the in case of two-dimensional drawing, so we are done it like this. Okay, so after that, at some angle only it is oriented. Okay, so now you're going to calculate the effective depth to be provided in case of counterfort retaining wall. Okay, I'll show what is the effective depth, that and all I'll show in further. Okay, so if you see, we have calculated in the previous step minimum depth to be provided for the counterport support. Okay, now we are going to calculate the effective depth. So if you consider this thing, this is the effective depth. So this is the effective depth. So from this point to this point. Okay, so this is the depth of the counterport to be provided. How will you calculate the effective depth? You know, tan theta. Okay, considering the trigonometry properties. Okay, so what is the tan theta expression? Okay, for sine, cos, tan, there will be different sides is there, no? So for sine, what is this? Opposite by hypotenuse is for sine. Okay, similarly for the cos, it is adjacent by hypotenuse. For the tan, it is opposite by adjacent. Okay, so you know the value of opposite. Opposite. Okay, so the in the right angle triangle, so this is the opposite side. Okay, so the opposite side dimension is 7.8, that we have substituted, divided by the adjacent side. The adjacent side dimension is 4.05. Okay, that also you are substituted. Okay, 7.8 divided by 4.05, so 1.93. Okay, so that is the tan theta angle. Okay, so with this you are calculating the angle, which is angle of the counterport, in which angle the counterport to be provided. Okay, so it will be like this. Okay, so tan inverse, so tan inverse of 1 equal to, so the value will be like this. Okay, so the value is 62 point. So at the result, okay, so but if you solve the expression in trigonometry by using trigonometrical methods, you can get the angle as 62.5 degrees. Okay, so this is the angle. Okay, so which is made. Okay, 62.5 degrees. Okay, so after that you're going to calculate the effective depth of the counterport support. Okay, so for that, how will you do? You know, so 4050 sine theta. Okay, depth is equal to 4050 sine theta. That is the width of the yield slab into sine theta minus effective depth. Okay, so usually the effective depth depends upon the types of the structural element. In case of counterfort, the effective depth will be sorry, that I'm taking my words back. Okay, so the effective cover. Okay, so the effective cover depends upon the structural element. Okay, so it depends upon the structural element. Okay, if you consider the beam, that is different. If you consider the column, that is different. Now likewise, the counterfort, you can take some dimension of effective cover. Okay, so probably by 25 mm to 30 mm. Okay, so you take, so after that, the effective depth is calculated like this. Okay, using this expression, using this expression, the effective depth is calculated. So this is the depth to be provided. Okay, actually, 3535 mm. Okay, so that is 3535 mm is the effective depth to be provided in case of counterfort support. Okay, in case of counterfort support, which is much greater than the 13, that is 1319 mm, which is calculated in the previous step. That is the minimum depth. Okay, so the minimum depth to be provided is 1390 mm, which is but we're going to provide the actually effective depth as 3535 mm. Okay, so which is much more than greater than this value. Okay, so we have calculated the effective depth also. This steps repeated again. Okay, so like we have done it in the design of stem and design of toe slab and heel slab, so mu divided by bd square. Okay, so this is the parameter to be calculated to refer the value area of steel in the design aid, that is SP16, design aid SP16. So okay, so mu. Okay, so you substitute the value of moment which we have calculated in the previous step, that is 2135.6 into 10 power of 6 is nothing but you are converting the kilonewton meter into newton mm. So that's why you are converting this divided by bd square. B is a breadth. Okay, so breadth of the counterfort is 400 that we have assumed initially. After that, effective depth of the cantilever. So the effective depth of the counterfort, that is 3535 square. Okay. So then the parameter value is mu divided by bd square is equal to 0.427. Okay. Considering based upon this value, you can refer table number 2 of SP16. Okay. So then you can get the percentage of steel. From the percentage of steel, you can get the area of steel. Okay. How will you get the area of steel from the percentage of steel value? Can anyone tell? So you got the value of percentage of steel. So you need the area of steel value to be provided. How will you do that? This you have done it in the cantilever wall design itself. Okay. So can you get my question? Okay. So you got the percentage of steel value, that is PT is 0.12 percentage. Okay. So from the PT value, you should calculate the area of steel value. Okay. Capital AST. How will you do that? So we have done it in the several times. Okay, so while while you are designing the stem, or else while you are designing the toe slab or heel slab, you could have done that. Okay, so the same question I'm repeating. Okay, so can you is my question is clear to you all? So you got the value of percentage of steel. How will you do the area of steel calculation? Yes, someone. Yes, answer me. Can you able to get the questions or not? Are you listening?
Yes, sir.
Yeah, answer my question. Shall I proceed? But you should answer this because several time it is repeated in the that theory classes. Okay, DSCPM. So I'll say once again. Okay, have a note. Don't forget hereafter. So Aravind sir has covered no, so that portion. Okay, okay. So there is a expression. So can you all able to see the screen?
Yes.
Can you all able to see the screen? Okay. So this is the expression percentage of steel, that is PT is equal to 100 AST divided by PD. Okay. So this is the expression. By using the expression, you can get the details. Okay. So you substitute the value of PT. Okay. That is 0.12 percentage. So after that, area of steel. Okay. Only you know. So that is the unknown value. Okay. You cannot have this value now. Okay. This is the unknown value. Okay. So after that, the value of B and D, you know. So the breadth of the curtailment is 400 mm. The depth of the curtailment is we calculated just now. Okay. So 3535 mm. Okay. So all the values you know except the value of AST. Okay. So you take the BD on the numerical side, and you take the 100 at the denominators. Okay. So 100 will be on the denominator, and the B and the D will be on the numerator. Okay. So in this case only AST will be there. Okay. So this and all gone. Okay. So by this step or by this method you can calculate the area of steel. Based upon the area of steel, you know, so you can calculate the reinforcement to be provided in the curtailment. Okay. So now I'm going to show different kinds of reinforcement are provided. Okay. So if you see here, the minimum area of steel to be provided. Okay, so why you have to go for the minimum area of steel? You know, like you provide the curtailment reinforcement. Okay, so you provide the curtailment reinforcement, but the inner side also has to be reinforced. Okay, so that's why we go for the minimum area of reinforcement, that is 0.85 BD divided by Fy. Okay, so you got the minimum area of steel. So based upon this, you provide 4 numbers of 22 mm diabars plus 4 numbers of 22 mm diabars. Okay, at the both the directions. Okay, so after that, the percentage of after providing these two kinds of reinforcement, your percentage of steel is 0.21, but it is one enough that if you provide 0.12 percentage itself. Okay, so you are providing the additional reinforcements only. Okay, so after that, so as I told about the curtailment reinforcement, so there are different kinds of reinforcement to be provided in the counterfort support. Okay, so curtailment reinforcement. Okay, so the curtailment reinforcement will start from here and it will go like this and it will tie like this. Okay, so it will tie the all the elements. Okay, it will tie the stem. So it start from the stem and it will cover overall counterfort, and it will end like this. Okay, like a hook. Okay, it will end like this. Okay, so this is the curtailment reinforcement to be provided on the one direction. Okay, so on the other direction only half of the curtailment is provided. In the similar way, it will start from here. Okay, actually it will start from here and it will go to the offer direction, up to offer length. Okay, up to which length you can go for the curtailment, you know. So root of h is nothing but root of overall height of the stem. Okay, so the overall height of the stem is 7.8. Root of 7.8, the value is 2.79 meters. Okay, so from the bottom to the 2.79 meters, you can provide the reinforcement. Okay, so curtailment reinforcement. Then so after providing the curtailment reinforcement, you know, so what are the other kind of reinforcement to be provided, you know? So the inner side of the counterfort also has to reinforce with the supplementary reinforcement along the vertical as well as the horizontal direction. Okay, so this reinforcement is provided. Okay, so this is the two different kinds of reinforcement provided in case of counterfort support of retaining wall. Okay, so I'll show it one more time. Okay, can you all able to see the screen?
Yes, sir.
Yes, sir.
Yeah. So the curtailment reinforcement provided on the surface. on the both the directions also. Okay, so like this, the surface of the reinforcement is curtailment reinforcement. Okay, so it will be provided like this along the x direction. If you consider along the y direction, it starts from here and it will go like this and it will tie like this. Okay, so during due to that provision, it ties, actually it ties the all the elements. Okay, so from the stem it travels to the counterfort and it ends in the heel like a hook. Okay, similarly from here also the counterfort is provided to the some distance. Okay, so that distance is decided based upon the height of the stem. Okay, so our height of the stem in our case is 7.8 meter. Okay, you just don't confuse. In the previous case of cantilever retaining wall, the height is 5.2 meter, but in this case 7.8 meter. Okay, so root of h, that is root of h, that is root of 7.8. It will have some value like 2.45 something, I think. Okay, so 2.45 meter. Okay, so root of 7.8 meter is equal to 2.45 meter. Okay, so this is the way. So this is the way, that is the surface reinforcement or curtailment reinforcement. So in one kind it is provided like this. It starts from the ear and fully it is reinforced. Okay, again the reinforcement starts here and it ends to some distance. Okay, that distance is called 2.45 meters. Okay, so after that there will be so therefore the surface of the counterport support is reinforced with the curtailment bars. Okay, so after that this portion is there, no, so this particular portion also has to be reinforced by supplementary reinforcement, so along the vertical direction as well as in the horizontal direction. Okay, likewise. Okay, so this reinforcement detailing also we will be seeing. Okay, so as of now, we have completed the design of the counterfort part of retaining wall. Okay, then we will draft that particular counterfort. That is the structural detaining of the counterfort retaining wall. Retaining wall will be done in the CAD software. That is AutoCAD software. Okay, so we will do it that that portion also.